come and participate in one of the Paradigm summer schools. I've heard a lot of really good things about them. So hopefully, you guys are all having a great experience as well. So what I wanted to do today is to tell you a little bit. So what I'm going to primarily focus on are 2D materials, and specifically 2D semiconductors, right? I have in the past worked on 3-5 materials, and I'll tell you a little bit about like what some of the differences are between 3-5s and 2D materials in terms of material synthesis. So my background, I should just tell you a little bit. My background is in materials synthesis, right? So I've worked primarily on compound semiconductor heteroepitaxy. So things like gallium arsenide, gallium nitride, and the technique that I primarily use is chemical vapor deposition. So I'm going to tell you about some of the work that we've been doing in chemical vapor deposition of 2D materials. But let me start off by just going back to, because that will help you to appreciate what some of the growing interest in 2D materials is. Okay, so you've had some really great talks this week from people like Jim Speck, right? Mike Spencer, so Lourdes Salamanca-Riba, right? And they've all talked about probably about gallium nitride materials, right? Compound semiconductors. So if you just think about the fundamentals of compound semiconductor epitaxy, right? One of the important rules of thumb is lattice matching, right? Anytime you're going to make a heteroepitaxial structure, you need to be very concerned about the lattice constant of the epitaxial layer, right, and the substrate. And this is what I would call the guidebook for heteroepitaxy, right? So this is a plot showing the band gap energy of the semiconductor versus the lattice constant. So when you're designing a semiconductor heterostructure, say, for example, a multiple quantum well structure for a light emitting diode or laser diode, or a multi-junction photovoltaic cell, right, where you need to stack a bunch of materials with different band gaps, you have to pay close attention to the lattice constant and lattice mismatch, right? Ideally, you want the film that you're depositing on the substrate to have the same crystal structure and the same lattice constant, right? But typically that isn't the case. And so that can lead to strain in the epitaxial layer if they're mismatched. And then ultimately, if the strain is too much, then it's energetically favorable to form defects like dislocations at the interface, right? So the rule is you must manage your lattice mismatch, or you need to manage the defects. And maybe you saw this in some of the earlier talks on gallium nitride. Gallium nitride heteroepitaxial films are typically full of defects, right? There's a lot of defects, but the fundamental properties of gallium nitride are not impacted as much by defects as in other semiconductors. Right. So this is sort of the rule that I worked with for many years in my career, and I really focused on, thinking about substrates and things like that. But within the last decade or two, there's a new class of materials that's come out. These are 2D materials, right? So these are things like graphene, right? So if you look at something like graphite, it has this structure in the bulk where you have sheets of carbon atoms that have sp2 bonding, right? And these sheets are held together by weaker van der Waals forces. So you can isolate a single layer, which is graphene, right? And graphene has some pretty remarkable properties. Similarly, there are other classes of layered materials like moly disulfide, which also has this layered structure where the sheets are held together by van der Waals forces. You can isolate a single layer of moly disulfide. And a lot of the initial excitement in the field and the continuing excitement has to do with the fact that you can take these monolayers, you can stack them together, right? And you can form heterostructures without the constraints of lattice matching, right? So now we don't have to worry about forming chemical bonds between the layers. and making sure that the atoms all line up, right? Now we can stack layers that have different lattice constants on one another. And I call this the Lego picture of 2D heterostructures. This has generated a lot of excitement in the field, and it's actually, there's a lot of really good fundamental physics that comes out of stacking 2D materials. But what I want to get across is when we're thinking about epitaxy, it turns out that lattice matching still matters, right? So I often am asked, like, well, why do you care about the lattice constant of the substrate when you're depositing these films? It shouldn't matter because these are van der Waals forces. Well, I'll show you later in my talk that it does matter. All right. So, but nevertheless, the interest in this class of 2D materials stems from the fact that they have a very wide range of electronic properties. So you're talking about materials like graphene, right, which is a semi-metal. On the other side, you have materials like hexagonal boron nitride, which you can make as a monolayer sheet as well. And this has a band gap of about 6 electron volts. So, an insulator basically. And then in between, there's a whole variety of 2D materials that are semiconductors, right? Some elemental semiconductors like black phosphorus, which has a narrower band gap. Moly disulfide that I mentioned already, which has a moderate band gap. And what I'm going to talk about primarily today is this class of 2D semiconductors called the transition metal dichalcogenides. So that includes moly disulfide, but there are also others like tungsten diselenide and related compounds, right? So I want to tell you why there's interest in this class of materials, both from the fundamental properties of the 2D layers, but also for some pretty significant applications. All right, so let's just start off talking about monolayer moly disulfide. So what makes it interesting? Okay, so this is some early work in like 2009 and 2010, where, shortly after graphene was discovered, right, after it was isolated, and then people found out that there were all these really unique properties, they started looking at all these other layered materials. And so moly disulfide was one of the first ones that was investigated. So it was predicted that if you decrease the number of layers of moly disulfide from a bulk crystal, right, down to a single monolayer, the band gap would change from being indirect gap here in the bulk to being direct gap in the monolayer. So that was predicted by DFT, and it was experimentally verified, right? So the consequence of this is that when you have a direct gap semiconductor, it emits light very efficiently, right? The electrons and holes can recombine readily. And so, for example, if you do photoluminescence measurements on moly disulfide, the photoluminescence quantum efficiency is much greater from a monolayer of moly disulfide than it is from a bulk crystal, right? So really interesting, right? Now you can have efficient light emission just from a single layer of material that's only 3 angstroms thick, right? Okay, but even more interesting properties. All right, so if you take a look at the Brouillon zone of something like moly disulfide, right? You have the direct gap that I mentioned in the monolayer, and it occurs at the K point, right? These K points. But monolayer moly disulfide lacks inversion symmetry. So these K points aren't equivalent. You have these inequivalent K points, right? In addition, because you have d orbitals in the molybdenum atom, you have very strong spin-orbit coupling in these materials, right? So the consequence is that both the conduction band and the valence band valleys are split as a result of the spin-orbit coupling, but you get larger splitting in the valence band. All right, so you have these alternating valleys that have opposite spin polarization. And it turns out you can selectively populate these different valleys using circularly polarized light, right? So depending on whether it's left-handed or right-handed, you can populate either the K or the K prime valley, right? And this is a whole field of study which is called valleytronic. So you may have heard people refer to this field of valleytronics. That's what it's all about, right? So lots of really interesting physics there. Other interesting properties are that when you shrink these materials down to just a single monolayer, excitons become very important in terms of light absorption and light emission. All right, so traditionally, we're usually working with bulk semiconductors, right? Gallium arsenide or gallium nitride, or even a bulk crystal of moly disulfide. If you look at the binding energy of electrons and holes in a bulk crystal, the binding energies are typically pretty small. So on the order of kT, like 25 millielectron volts, right? And that's because if you have an electron and a hole in a bulk semiconductor, they're pretty well screened, right? And so as a result, at room temperature, we typically don't see a lot of absorption or light emission due to excitons, right? It's usually band to band or defect to band, right? But now, whenever we shrink down these layers to a single monolayer, the electric field lines of the electron-hole pair extend beyond the physical thickness of the 2D layer. And the consequence of that, as we saw, is that it makes the material become direct gap, but this also significantly increases the binding energy of electrons and holes. So typically, in a monolayer TMD, the binding energy is a few hundred millielectron volts, right? So at room temperature, light absorption and light emission is all dominated by exciton transitions. So for example, this is a room temperature photoluminescence spectrum from moly disulfide. And this is showing the different transitions that you can have between the conduction band and the valence band, right? The split valence band. And you can see that you can fit this room temperature spectrum to exciton emissions associated with these different transitions, right? So the optical properties are much richer when you have a monolayer material than you might have in a bulk semiconductor, right? So that makes it interesting. But now I mentioned you can start stacking these materials, right? So what happens is not only can you have electrons and holes be associated with each other in a single layer, you can also have holes and electrons become associated with each other between layers in a heterostructure, right? These are referred to as interlayer excitons. So you can have recombination occurring between your moly disulfide and your tungsten disulfide here, right? So now you get additional emission peaks that arise because of these interlayer excitons. But then things get even more interesting because now you can also change the relative orientation of one layer relative to the other, right? And this is like an emerging area in physics, looking at the properties of twisted bilayers and Moiré superlattices, right? So you may have encountered this in some of your work, right? So the interesting thing here is that as you change the relative orientation, that's going to change the coupling between the layers, right? It's going to change the overlap of orbitals, and so that gives rise to other emission peaks. A lot of really interesting properties. Okay, so just from fundamental physics, there's a lot of really interesting stuff going on in this 2D area, specifically 2D semiconductors. But what are they good for, from a practical perspective, right? People always ask me. So, all right, it turns out that they may be very good for a very important application. So earlier in the week, you had a talk about the CHIPS Act, right? There's, this flurry of activity related to semiconductor transistors, right? So this all goes back to, our MOSFET device that I'm showing here, right? So, in a MOSFET, you have source, drain, and gate. You're modulating the gate voltage to change the current between the source and the drain, right? It's basically a switch, just turning it on and off by modulating the gate. But now you want to put a whole bunch of switches together on a wafer, right? So that's the name of the game in the semiconductor field. And you're probably all very aware of Moore's law, right? So Moore's law says that the number of transistors and resistors on a chip doubles every 24 months. And Moore's law has driven the semiconductor roadmap for decades. right? So it's the scaling law that's been used for these planar MOSFET devices. So this is a cross-section image of a planar MOSFET, right? Here we have the source and the drain and the gate, right? And this is from the 32 nanometer mode. So that roughly correlates with the gate length of the device, right? The sort of the length of this gate region that you have. Okay, so 32 nanometer node was about 2009 timeframe, right? And right about that, that time frame is when the problem of short channel effects started to develop, right? So the problem is, as you start shrinking that gate length smaller and smaller and smaller, it gets more difficult to turn the device on and off, to controllably keep it off without having some leakage current, right? So electrostatic control of the channel became the name of the game, right? And these short channel effects start to occur. They become more problematic when the gate length, or when the channel length that's shown here, becomes greater than about 3 times lambda, which is a characteristic length, right? So this lambda is proportional to properties of both the semiconductor channel, which is T sub s and epsilon sub s. So this is the dielectric constant of the semiconductor, the thickness of the semiconductor, the dielectric constant of the oxide, and the thickness of the oxide, right? So you can see here, all right, if you want to, reduce the effect of these electrostatic problems, you need to reduce the thickness of the oxide, reduce these thicknesses. You want to increase the dielectric constant of the oxide and reduce the dielectric constant of the semiconductor, right? So this led to a lot of work. Let me just move forward here. Okay, so this led to a lot of work in looking at different oxides, right? So originally, silicon dioxide was used. It's a good native oxide, but it doesn't have a high dielectric constant. So the field switched to hafnium dioxide, to high K dielectrics, right? All to get around this problem with short channel effects. And that kind of took us through. So this is like the happy physical scaling region, which occurred maybe up until 2010, right? But then to try to get around this problem even further, the semiconductor industry switched to this FinFET geometry. So now, rather than just having the gate on one side of the semiconductor, you wrap it around 3 sides, right? That gives you improved electrostatic control. You combine that with hafnium dioxide, things look pretty good. You continue your scaling. But now we've reached this point where we can no longer continue to scale the dimensions based on this FinFET geometry. And so this is the point that the semiconductor industry is at right now. Like, what do we do beyond these phisical scaling limits? So some of the things that are being looked at are other semiconductors like silicon germanium, 3.5s, carbon nanotubes, different geometries. So there's this gate all around geometry shown here, which is what most of the semiconductor companies are working on. So now you're wrapping the gate dielectric all the way around the channel. That improves the electrostatic control even more. But the problem with silicon is that if you try to continue scaling it, if you try to continue to shrink down the thickness of silicon, you start to have some fundamental problems. And that's reached at about a thickness of 5 nanometers. So this is where 2D materials come in, okay? Oh, sure, yeah.
Show that the gate doesn't actually change.
Yeah.
So why do we call these the 2 nanometer node and stuff?
Yeah. So right. So you're not physically scaling the gate width or the channel length, but you're still packing more transistors into a given area. So it gets complicated because it really has more to do with like the density of transistors than the physical length of the channel. So yeah, so just something to be aware of. It doesn't actually correlate with the physical gate length. So as I said, this is where 2D semiconductors come in, right? So they're another material that's being considered for future generation gate all around or nanosheet FETs. And the reason why is because there's some really compelling properties of 2D semiconductors. The first and the most compelling property is that they're nearly atomically thin, right? So something like moly disulfide, if you're just talking about the monolayer, it's only 3 atoms thick, right? It's sort of like the ultimate, nearly the ultimate thinness, right? Ideally, maybe you just want a single atomic layer. But moly disulfide is pretty close, so it's really thin. And furthermore, it's got passivated surfaces, right? Because it has these van der Waals surfaces. So you don't have dangling bonds like you have on silicon, which is where all the work in like developing an oxide and having a really good quality interface comes in, right? You don't have to worry quite as much about dangling bonds, but the interface is still important, I should say. But probably the most intriguing characteristic is that when you scale down, when you start scaling down the thickness of silicon, as shown here, this is the electron and hole mobility in silicon, it really drops off, especially once you get down less than 3 nanometers. But the transition metal dichalcogenides, like moly disulfide and tungsten diselenide, are able to sustain good transport properties even less than 1 nanometer in thickness, right? So that makes people excited, like, okay, here we can, really aggressively scale down the thickness of the devices. But also, you could envision being able to stack these nanosheet transistors. So now, rather than having your P-type and N-type devices, which is your CMOS next to one another, you could stack them vertically, right? Or you could start to monolithically integrate tiers of transistors in the 3rd dimension. So that's really where like the semiconductor field is going. They're starting to go to making vertically stacked devices, really trying to compact things, again, to put more transistors into a given area, right? So this is where there's excitement in terms of potential applications for 2D semiconductors. But also, as I mentioned, they have really interesting optical properties, right? And in particular, an interesting thing about these monolayer TMDs is that they have very large absorption coefficients. So this is a plot of the absorption coefficient of TMDs and some of the more common semiconductors that we work with. So you can see the absorption coefficients are very large. So that makes them of interest for things like photodetectors, right? But now you can take your photodetector and maybe more easily integrate it onto a silicon CMOS chip. So you can combine your photodetector, maybe image sensing with logic, right? So this is a field that's often referred to as like more than more. So enhancing the functionality of electronic devices. And maybe 2D materials will find some applications there, okay? So I spent a fair amount of time there, but I just wanted to give you a good sense for why there's a lot of interest in 2D semiconductors and how they fit into this whole field of semiconductors for future generation transistors. But one of the problems is all of these interesting properties and these interesting applications occur in a single monolayer, right? So how do we make single monolayers? So the technique that is still the most commonly used method is to exfoliate a bulk crystal. So you start off with the bulk crystal of something like moly disulfide, and then you use an adhesive, and I just put Scotch tape here to be a little funny, but the basic idea is that you're peeling off layers, right? And typically you have to do this a number of times, and then eventually you'll have a flake that is just a single layer. This is illustrated here for graphene, but it's the same approach for 2D semiconductors as well. So of course, the drawback is that the flakes that you get are sort of irregularly shaped. They're small. It's not a real reproducible process. But I don't want to poo-poo it because this is, being able to make monolayers by exfoliation has really advanced the field rapidly, right? So you can get a bulk crystal, you can get a monolayer of molybdisulfide, do some really nice studies, get a Science and Nature paper. You don't have to have a fancy MBE system or an MOCVD system, right? So it's really enabled the field to accelerate quite a bit. But now we're getting to the point where we want to look at these materials for applications, right? And exfoliation is not going to cut it. So, part of the challenge is that it's actually tricky to grow bulk crystals of these transition metal dichalcogenides and get like crystals that would be suitable for making wafer scale materials, right? Paradigm here at Johns Hopkins, they're experts in bulk crystal growth, but they appreciate the challenges. That one of the techniques that's used is chemical vapor transport. This is carried out in a sealed quartz ampule. You put the source material on one side of the ampule. You also introduce a transport agent because it's difficult to volatilize the molybdenum containing sources or the tungsten containing sources. You put your ampule into a tube furnace, you let it sit for about a week, and then you'll start to crystallize on the opposite end that's a little cooler, right? And so this works really well, and you can make a whole variety of TMDs and other chalcogenide crystals using chemical vapor transport, but it's really tricky to get large crystals this way. Yeah. So this is a crystal that I got from Bruce Parkinson. He's a faculty member at the University of Wyoming. He did a lot of work on this class of materials back in the 1990s because there was interest in them for photovoltaics. So he was at DuPont. They had a big effort in doing chemical vapor transport growth, and he sent me a bunch of crystals. And this is one that's about 1 inch large, which is pretty big for a CVT grown crystal, but not big enough for the semiconductor industry, right? So this motivates some of the work that we're doing at our 2D Crystal Consortium facility, right? So what we want to do is to apply the traditional principles of epitaxy, but now to 2D materials. Okay, so I was telling you that, oh, lattice matching doesn't matter. Well, it does. So there are two main approaches that are being used to make wafer scale TMD monolayers. So one is to start off with a substrate like silicon that has an oxide on it, so maybe SiO2 or another dielectric, and then deposit the material using chemical vapor deposition or another vapor deposition technique. But as we know, if the surface is amorphous, then we're going to have domains that are sort of randomly oriented. And whenever these domains grow and coalesce and form a film, it's going to be polycrystalline. Even if it's a single layer, it's going to be polycrystalline. It's going to have high angle grain boundaries. And those high angle grain boundaries will scatter electrons, will scatter carriers. And generally, we want to avoid that. So we have to get back to epitaxy, right? We need to be concerned about the substrate. Because ideally we want all of these domains to be ordered perfectly on our substrate so that when they coalesce, we get a single crystal monolayer film over a 300 millimeter wafer or something like that. So that's the ultimate goal. The reality of it is, as with any epitaxial process, things aren't perfect, right? So there will be twin boundaries that I'm showing here. These are oppositely oriented domains. When coalescence occurs, there might be some pinholes. You can also start to get a second layer growing on the first layer. So this is sort of the reality. And what I want to do is just kind of quickly share with you some of the work that we're doing in this area, looking at epitaxy on single crystal substrates. So as I mentioned, the lattice constant of the substrate is important, and the crystal symmetry of the substrate is important. So the transition metal dichalcogenides have hexagonal crystal structures. So for a substrate, we have to also look at something that has a similar crystal structure. So things like C-plane sapphire, silicon carbide, the nitrides that you've heard about, and also graphene or graphite are all suitable substrates, right? we've focused primarily on C-plane sapphire. If you just directly compare the lattice constant of moly disulfide and C-plane sapphire, it looks like it has a pretty big mismatch, but there's commensurability between the lattices. So 3-unit cells of moly disulfide match up pretty well with 2-unit cells of sapphire, and that reduces the effective mismatch. So it makes it a reasonably good substrate for TMD. Also, it's fairly chemically stable and thermally stable at high temperatures, right? But there is this problem of twinning, which is common in other epitaxial systems, right? So because these materials lack inversion symmetry, if you have oppositely oriented domains and they grow together and coalesce, they form an inversion domain boundary, or sometimes it's called a mirror twin boundary. And this type of boundary has metallic character. So even though it's a low angle grain boundary, it's still not great to have these inversion domain boundaries in your films. Okay, so what are some of the things we should think about in terms of epitaxy of this class of materials? So we have transition metals and we have chalcogens that comprise our material. And they have very different physical properties, and that introduces some challenges into a vapor deposition method. So for example, we have things like molybdenum or tungsten. They have high melting temperatures, right? The vapor pressure is really small for something like molybdenum until you get up to like 1500 degrees C, right? So low vapor pressure transition metals. And then on the flip side, we have the chalcogens like selenium and sulfur. These have low melting temperatures, high vapor pressures, even at low temperatures. So you sort of have a mismatch just in terms of the physical properties there. Now, when you're talking about epitaxy, there's a rule of thumb. The growth temperature for the material should be at least half of the melting temperature of whatever it is you're trying to deposit in order to get good crystallinity. This comes out of like the zone model of microstructure development, which you may have covered in a class somewhere. It basically just has to do with the bond strength of the material, right? So for something like moly disulfide, it has a melting temperature that's almost at 1200 degrees C, right? So as a result, we know that the growth temperature we're going to need has to be probably 600 degrees C or higher, right? So we need to grow these materials at fairly high temperatures, but at those high temperatures, the sticking coefficient of the chalcogens is going to be really low. So you have these trade-offs. So typically what you have to do is use high growth temperatures, but you need to use a large excess of the chalcogen in order to get stoichiometric growth. And then because we're trying to grow just a single monolayer, we need to grow fairly slowly, right? So that makes things a little challenging. So we approach this by just, again, sort of going back to our fundamentals of deposition with metal organic chemical vapor deposition. So we used systems that you might use for something like gallium arsenide or gallium nitride, right? So these are cold wall reactors shown here. A lot of work in CVD growth of transition metal dichalcogenides is done using a hot wall reactor. And you put your source materials directly into the reactor and vaporize them that way. That works great, but it's difficult to get good uniformity over large areas. And again, we're trying to match some of the requirements for devices. So we're using MOCVD. These are photos of 2 of the systems that we have in the 2D Crystal Consortium facility at Penn State. As I mentioned, these are cold wall reactors, right? For the sources, we use metal hexacarbonyls shown here, and we use hydride, hydrogen selenide and hydrogen sulfide for the chalcogens. The downside is they're toxic gases, so you have to have the infrastructure to be able to handle them. But we've been doing nitrides and arsenides in that lab, so we kind of had all that infrastructure, so it wasn't as much of a problem. The benefit is you don't have carbon in any of your chalcogen sources, and so you don't end up with carbon in your films. I should mention that even though we have carbon CO ligands here, they don't really decompose. They just kind of stay in the gas phase and go away, so they're not as much of a problem. So just a snapshot of some of the conditions that we use. So as I mentioned, high temperatures, high chalcogen to metal ratios. And then I just want to quickly step you through like some of the research that we've done looking at epitaxial growth of these materials. So this is an example of tungsten diselenide epitaxy by MOCVD, where we developed this three-step process to grow on our sapphire substrate. So we have a nucleation stage where we introduce both the tungsten and the selenium source, and we get nuclei, like small clusters on the surface, right? And then we just switch out the tungsten and we allow the surface to ripen. So we allow the tungsten to diffuse on the surface and form small triangular islands. And then we reintroduce the tungsten precursor, but at a lower flow rate, so we can laterally grow these triangles, these triangular domains, so we get a coalesced film. So this is some early work using this three-step process. This is a series of SEM images for different lateral growth times, and the dark features are the tungsten diselenide triangular domains on the sapphire. And you can see as we increase the time, they grow in size, they start to coalesce. And after about an hour, we have a nearly fully coalesced monolayer film, right? The main thing I want to point out from these images is that if you take a look at the orientation of these tungsten diselenide triangles, you can see that they have primarily two orientations. These are this is the 0 degree and the 60 degree domain orientation on sapphire that I mentioned earlier. And whenever these domains coalesce, they form an inversion domain boundary. So, ideally, we don't want to have those things. So we adjusted our growth conditions, went up to even higher temperatures and higher chalcogen to metal ratios. And what we found is that we started to get a preferential orientation for the tungsten diselenide. So in this case, and I've kind of color-coded the domains here, the red ones have the 0 degree orientation and the blue ones have the 60 degree orientation. And you can see that about 86% have this 0 degree orientation, which, looks good. All right. So we wanted to understand why we were getting this preferential orientation, because ultimately we want to have all of our domains have that orientation and, ideally completely get rid of inversion domains in the films. So if you take a step back and you just think about the sapphire substrate, the sapphire substrate it's nominally on axis of the 0, 0, 0, 1 plane, but it's miscut by a slight amount, by 0.2 degrees. And as a result, you have these steps, right? You have steps and terraces on the sapphire substrate. This is an AFM image of what the sapphire surface looks like. And we know from prior work that the steps on the sapphire can serve as preferential sites for nucleation, right? So we wanted to study this in more detail, and we can do this using this three-step process because we can stop right after nucleation or after a short time of lateral growth, and we can look at where the nucleation is occurring. And it turns out that the tungsten diselenide nuclei are indeed, most of them are forming at the step edges, as shown here. And if you grow for a little bit of time, so they start to take a triangular shape, you can see that they start to align on the step edges. But the interesting thing is that they all seem to be aligned on the top edge of the steps rather than the bottom edge of the step shown here, which is the more common location if you're talking about like a step-directed growth mechanism. So we thought this was interesting, reached out to our theory collaborators in 2DCC and asked for their help in trying to explain why we would get nucleation on the top of the step versus the bottom edge of the step. So they started off just by considering the sapphire surface when you have a step edge present. So the sapphire as received is terminated with hydroxyl groups. And then we take the sapphire, we put it in our MOCVD system, we heat it up to 800 or 1000 degrees C under hydrogen. And what happens is the hydrogen reacts with the hydroxyl groups and it forms water. So we start to remove oxygen from the surface in the form of water as a result of this high temperature hydrogen exposure. But the hydroxyl group loss is not equal across the whole surface when you have a step edge. It's most favorable to occur at the top of one of these steps, and the least favorable location for it to occur is at the bottom edge of the step. So this is giving us, some clue that there's probably going to be differences in the surface termination of our sapphire, depending on the conditions that we're using for growth. So they further developed this model by considering that whenever you've removed the hydroxyl groups and you have just aluminum termination, you're going to end up passivating that aluminum terminated surface with selenium. And we have evidence of that from cross-section STEM images shown here. So this is the tungsten diselenide, this is the sapphire. And you can see that there's this region right here, right at the interface, that has a different contrast. If we do EDS, if we take an EDS line scan right across that interface, we see an increase in selenium right at that interface. And there have been prior studies that have suggested that you get chalcogen passivation of sapphire. You sort of need that because you aren't forming chemical bonds right across the interface. You have more van der Waals epitaxy, so the surface has to be passivated in some way. So they assumed that the surface was passivated, and they considered two different situations. In one case, the entire surface is going to be fully passivated with selenium. And if you allow the system to relax in the presence of a small cluster of tungsten diselenide, what you find is that the bottom edge of the step becomes the preferred site for nucleation to occur, right? But if you have incomplete removal of oxygen from the surface, so you still have a remnant of oxygen left at the bottom edge of the step, then the top edge of the step becomes the preferred site for nucleation. So good thing to do when you are working with theorists is to test their models. So we did this just by changing the growth pressure when we were growing the tungsten diselenide. So originally we had been using 200 torr, and this gave us the preferred 0-degree orientation, which means the nucleation is occurring at the top edge of the step, right? That's consistent with their model, where if we still, if we haven't completely removed the hydroxyl groups, then the top edge is going to be the preferred site. But if we increase the reactor pressure, we're effectively increasing the chemical potential of hydrogen and hydrogen selenide. And so we would more completely passivate the surface. They predict then that the bottom edge of the step should be the preferred site. And we indeed see a complete flip of the preferred orientation. So now we have 60-degree oriented domains, right? So the upshot of this work, what this really taught us is that to understand and be able to control the direction of TMD domains on a surface, not only do you have to understand the structure of the sapphire, like the step structure, but you also have to understand the surface termination. And that's going to change depending on the particular deposition method you're using, right? If you're using MBE or MOCVD, but also the conditions you're using, right? Because that's going to change the extent of hydroxyl group removal, chalcogen passivation. So bottom line is a lot going on there, right? But nevertheless, we can use this process to make nearly fully coalesced monolayers on sapphire, and primarily on 2-inch sapphire is what we're using right now. This is just an example for tungsten diselenide on sapphire. There are some small pinholes in the film. As I mentioned, it's tricky at this point to get it perfectly coalesced. But these are nice heteroepitaxial films, right? You can do in-plane X-ray diffraction. You can see that they're well aligned epitaxially. You can measure the full width at half maximum of the peak, just like we do for 3.5s, right? Not too bad. It's 540 arc seconds. Also, since these are monolayers, they efficiently emit light. So we do things like measure the photoluminescence as a function of temperature and look at emission from excitons and defect-related luminescence. And that correlates with point defects in the films. We can deposit sulfides using a similar process. This is an example for tungsten disulfide, right? Again, if we control the conditions we can get the domains not all, but for most of them to have the same direction and minimize inversion domains in the films. And then you might be wondering, like, okay, now you have them on sapphire, what do you do with them then? So if you want to make devices, or if you want to do TEM characterization, you have to remove them from the growth substrate, right? So transfer is a big thing in the 2D field, right? You have to have some way to transfer these layers so you're not introducing wrinkles or other impurities. So a common method that's used, and the one that we typically use, is to do this water-based transfer. So the way that this works is you have your growth substrate, you spin coat PMMA on the surface, you scratch around the edges, and then you immerse your sample in water or maybe a dilute sodium hydroxide solution. And the neat thing is, because the film is weakly bound to the substrate, the water can get underneath the 2D layer and capillary forces will kind of just suck it up, right? And the 2D film with the PMMA will peel off of your growth substrate. So these are examples of tungsten disulfide kind of peeling off of sapphire, right, in water. And then you can transfer it to an oxidized silicon substrate, or maybe a device structure that you've already patterned, or a TEM grid. And I'm just going to very quickly, I'm going to skip through this. So we've done a lot of TEM characterization of these films, right? Because I told you, I made this big fuss about the fact that we don't want to have high angle grain boundaries. We want to minimize inversion domains. And the upshot is that we have been able to largely eliminate high angle grain boundaries. We still do have some low angle, sorry. Oh yeah, let me just show this one. Some low angle grain boundaries. So these are features that pop up in the dark field image. You can kind of see these regions that have a darker contrast here. Some of those are inversion domains. Some of them are actually translational line defects. So they're domains that have the same orientation, but they're offset by maybe like a subunit cell difference. So the lattices don't perfectly match, right? So there are still some low angle grain boundaries in these films. But nevertheless, we can make, you know, a whole suite of different TMD monolayers using this technique and using sort of the core principles of epitaxy that we've used for other 3.5s as well. Oh, yep. Yeah, that's a really interesting point. So we have not done extensive, so when we grow these, we typically do anneal them post-growth, just in the growth chamber. Mostly we do that because if we don't, we end up with some little tungsten or molybdenum particles on the surface. So we anneal them just to give those particles a chance to move around. But we're also very interested to study whether there's some motion of grain boundaries in these films as a result of annealing. We haven't really looked at that yet, but I think that's an interesting area as well. Okay, so let me just finish up by, oh, wait. Let me just finish up by telling you a little bit about the transport properties of these films, because I sort of put this in the context of FETs. So we have a collaborator, Saptarshi Das at Penn State, who's an expert in 2D devices. We give him a lot of material. This is some initial work that his group did, just comparing the transport properties of our MOCVD monolayer materials to what they would typically get if they just exfoliated a bulk crystal. And you can see that the transport properties are pretty comparable. Mobility is on the order of about 30 centimeters squared per volt second. That's pretty common with a lot of the CVD grown material in the literature, right? But they compare pretty favorably to what you would get from exfoliated flakes. So that looks promising. But the very nice thing about having these monolayers on a 2-inch wafer is you can start to make a lot of devices, and you can start to get statistical information on the device performance. And that's really what's needed in order to, push the field towards actual applications. So this is an example of a paper again, from Saptarshi Das's group, where they made a couple hundred FETs using moly disulfide and tungsten disulfide, right? And they were able to get statistical information on the device performance as they changed the channel length, and look at device-to-device variation. But then more recently, Saptarshi hasn't been, he's not satisfied with just a couple hundred FETs. So this is a recent paper from his group that was published in Nature, where they used these 2-inch monolayers to make monolithically integrated devices. So now you have 2 or 3 tiers of devices that are stacked one on top of another. And in each tier, there's about 10,000 FETs, so large number of FETs. The main interest here was to look at the performance of devices in, say, the first tier, the second tier, to understand the impact of like subsequent processing on the device performance. And the upshot is that the devices weren't degraded that much. So this is a really nice result. But with that, I'm going to finish off. So I think epitaxy is a promising technique, even for van der Waals bonded materials, right? It's still important. But now that we're trying to grow just a single layer on the substrate surface, we need to know a lot about the substrate, right? We need to really focus on understanding the structure, the chemistry of the substrate, because that's where the action is occurring. MOCVD offers a lot of advantages. So in terms of manufacturing, it's a technique that's used by the semiconductor industry, right? So it's fairly straightforward to scale it up to multi-wafer reactors. We're currently working on integrating in situ monitoring so that we can control our process a little bit better. But this is still a field that's in the early stages. So, I think there's going to be a lot more exciting developments coming up. Here's where we are right now. I showed you this at the beginning. We're nearly single crystal. But I think, if we just keep working on it, and especially the grad students, I think that, there's the potential to be able to make this technique that can be manufacturable. So with that, I just want to thank my group members and collaborators who contributed to this work. And of course, I have to thank the NSF for funding us, right, for both 2DCC and Paradigm. And of course, I have to give a pitch for 2DCC. So our MIP is focused on 2D materials primarily. So in addition to the transition metal dichalcogenides that I talked about, we in I guess I would call it quantum materials. So topological insulators, 2D superconductors, materials like Weil semi-metals, right? So a lot of interesting physics that can be done in this class of chalcogenide materials. So if you're interested in learning more, or maybe getting some hands-on training, specifically in the area of chalcogenide materials, get in touch, check out our website. We also have we don't have summer schools like Paradigm. We have an annual meeting, but we have a visiting scholar program for graduate students and postdocs to come on site and work in our facility. So if any of that is of interest, please let me know or get in touch. And with that, I want to thank you for your attention, and I'd be happy to answer any questions.
Wonderful. Thank you, Joan, for the night's talk. We're going to ask a question from one of our online participants first.
Sure.
So you showed this very nice process of getting the film off of the 2-inch wafer by essentially putting PMMA on and then soaking it in water. The question is, okay, you've now got it floating on the water or whatever it is. Oops. Now, what do you do next to transfer it?
Oh, yes. Okay. So actually, I left out a step. We also, on top of the PMMA, we put thermal release tape. So it's just another adhesive that goes on top of the PMMA. So whenever the 2D layer releases from the substrate, it's still on that thermal release tape, which provides more of a rigid structure. And then we just basically pick it up out of the solution, and we try to laminate it onto the substrate that we're transferring it onto. So sometimes we use like an actual laminating process, or if it's small enough, we just kind of press it onto the substrate, but it's fairly straightforward. But the challenge is really doing that without introducing bubbles, wrinkles, or other impurities.
Does then, so I mean, the MOCVD is obviously something that's more in line with what a wafer scale manufacturing process is. Is there going to be, does there need to be like another iteration of this whole like lift-off technique to get it to that level, or is it okay?
Yeah, so there are places like IMEC, which they're working on. There's been a lot of work on like wafer bonding methods, right? So methods to bond together dissimilar materials. Not that this is exactly the same, but you can use some of the same techniques of wafer bonding for this layer transfer process. So that's an approach that's definitely under development. But I should mention that there's a lot of work starting looking at selective growth of these materials. So if you can controllably locate, if you can control the nucleation on the substrate to a specific spot and just grow a small enough domain there, if you think about it, for like transistor devices, you don't need to completely cover the surface. You just need your semiconductor material in a specific location. So there's some work going on looking at like pattern substrates, ways to control the substrate surface to get the growth to occur just where you need it. That way you don't have to do transfer.
I noticed that you increased the pressure. You had more of your orientation 0 degrees. Why not lower it more? Or is that something you're working on?
Yeah, that's a good question. So I think probably about the lowest that we can practically go just with our process chamber is about 104. And we've gone down in pressure. We don't really see much improvement there. So yeah.
TMDs have other phases like 1T and 1T prime. For certain substrates or during any of the process, do you ever see other phases coming up?
Yeah, that's a really good question. So have noticed that if under certain conditions, we get molybdisulfide that we believe is the 1T prime phase, and that occurs when we're substoichiometric, when we're sulfur deficient. I think then it's more likely for it to want to form as 1T prime, I think, rather than 2H. Yeah. But usually we're focusing on 2H. So.
Once you have all the position figured out, how would you pattern period? Is it a regular photoresist?
Yeah, that's a good question. I think that's what's currently being used is still traditional. I mean, e-beam lithography is used, and you have your e-beam resists. I don't know that anyone is working on alternatives right now, but maybe that will be necessary.